Okay, so a homogeneous sphere of mass m and radius r is projected along the incline of angle theta with an initial speed v0 and no angular velocity omega 0. If the coefficient of kinetic friction is mu k, determine the time duration t of the kinetic of the period of slipping. In addition, state the velocity v of the mass center g and the angular velocity omega at the end of the period of slipping. Okay, so initially the ball is giving, or the sphere is given an initial velocity v v0. If we take this direction to be ex, then we're gonna say that's v0 ex. And omega is 0 initially, meaning that all the points on the body, they have the same velocity. In particular, this point P, the contact point between the sphere and the ground, has velocity also, VO ex, meaning that it's slipping. So what's going to happen is that if we draw the free body diagram of the ball, we have the weight acting on it, normal, and friction. Friction, which is gonna be opposite to this velocity of this point here, the friction force. And this friction force is gonna do work on the system because it's being applied at this point P, and this point P has non-zero velocity. The friction force is gonna do work on the system, which gonna deplete the system's energy. So the system at some point is gonna transition to rotating, where the velocity, rotating without slipping, where the velocity of point P becomes 0. We have to find we need to determine the time duration t of the period of slipping. Okay, determine the time duration t of the period of slipping. Okay, so we've drawn the free body diagram of the system. If I go through the steps, number 1 is the position vector of the center of mass. Here they call it G, I will call it C. RC is equal to x EX plus some constant R along EY, and VC is x dot EX. AC is x double dot EX. Next we have the free body diagram. The normal force is along EY. The friction force is minus mu k, the magnitude of the normal force, n times or along minus ex. So I have the minus already, and that's ex. And the weight is mg. So I'm just drawing the basis vectors and the direction of the weight. Oops. This angle here is theta, and so this angle here is theta. So the weight is mg minus cosine theta ey plus sine theta ex. Okay. Now the next thing I'm thinking about is which balance laws should I apply? Should I apply the balance of linear momentum, balance of angular momentum in their like regular forms, or in their integral forms, the linear impulse, linear momentum equation, angular impulse, angular momentum equation? Why am I thinking about that? Because they asked us about a time duration. So we're kind of looking at an interval. Let's look at the integral equations, and if it doesn't work, we'll go back to the regular equations. Okay, so the integral of f dt is m v c at t1 minus m vc at t2, t0, and here let us define what t1 and t0 are. Let t0 is the initial time, and T1 the time when you transition to roll without slip. Okay. And we know the velocity of the ball initially and the angular velocity of the ball initially at time t0. Okay, this is from t0 to t1. Okay, and the integral form of the sum of moments about c dt is the integral from t0 to t of I s c z z omega e z, well, omega at t1 minus I c z z omega at t0. Both of these are not easy. Very well. So here I know that omega at t0 is 0 and vc at t0 is just v0 ex. Okay, and I can solve for the normal force. That one I can do just by looking at F equals ma, not the integral form. Simple step just to solve for the normal force. Okay, so that's the normal force. Okay, now I can go back and plug in this equation. This one I only need to write it along ex. Along ey, we use it to find the normal force, which we did. So the along ex, we have that the integral from t0 to t, let me change colors. The integral from t0 to t of minus mu k, n is mg cosine theta, dot with the x, plus mg sine theta dt is equal to m vc at t1, which is basically x dot at t1. I'm gonna, well, x dot at t1 minus m v0. Notice here that these are all constants. So I can integrate just by taking the constants outside. I will get mg sine theta minus mu k cosine theta. I'm doing some rearranging. T minus t0, or t1 minus t0, which is what we want to find. This is the what we want to find, is equal to m x dot at t1 minus v0. This we do not know. So this is one equation, but it has two unknowns. We do not know the velocity at t1. If we did know it, then we can find this time interval, t1 minus t0. Okay, next let us look at the moment equation. The sum of moments about c, that's equal to, let me calculate this on this side before I plug it into the equations. mc is equal to the moment of the weight. The weight has no moment about c, but the normal and the friction force too. rp minus rc cross the normal plus the friction force. So rp minus rc is this vector, so minus r ey crossed with n ey minus mu k mg cosine theta ex, and that's equal to minus r mu k mg cosine theta easy. Okay, so I'm gonna take this value and plug it back here and fill up this equation to get the integral from t0 to t minus r mu k mg cosine theta. Say I've already projected along easy. Dt is equal to ICZZ omega at t1. Very well, and similarly, this integrand is also constant. So I can write it as minus r mu k mg cosine theta times delta t, t1 minus t0 is equal to ICZZ omega at t1. Very well. So now I have these two unknowns in this equation. This one, the time interval, and omega at t1. So far I have these two equations. Let me highlight them here. This one and this one. Two equations but three unknowns. Now we go back and we think we're looking specifically at the time t1 at which the ball transitions to rolling without sliding. And when the ball starts rolling without sliding, we know that there is a relationship between omega and x dot. At t1, when the ball rolls without slipping, or starts to roll without slipping at least, then we can say that Vp is equal to 0. Then Vc minus Vp is omega cross Rc minus Rp, and Vp is 0. Vc, which is x dot Ex, is equal to omega Ez cross Rey minus omega Rez, and voila, x dot is equal to minus omega r. This is our third equation. So now we can solve. I think everything is given. R mg theta. ICZ, that's the moment of inertia of a sphere about its mass center. So we can look that up from the tables. I think I have them open here. So the sphere, not the spherical shell, the sphere about an axis passing by a center, this moment of inertia is 2 over 5 mr squared. 2 over 5 mr squared. And I think we're good to go for this problem.